our choice for exercise 4 from our reference will be exercise 220 that we have here, which is an inclined beam that is trapezoidally loaded. 5 kips per feet as the largest load or as the P1, and 2 kips per feet as the P2, with a horizontal distance of 20, or a horizontal span of 24 feet and a vertical span of 10 feet. Okay, here we have a normal pin support, and here we have a roller support perpendicular to the inclination of the bar, right? So this is what we want to solve right now. Okay, so let's go straight to Robo and do that. Okay, so here we are. Obviously, again, it's the 2D structure, right? So we just need to click here on frame 2D to get started. Hmm, hoping that the computer doesn't keep us for long. Yeah, okay. So why this is coming, I just want to say that there are obviously some exercises that we will not be touching, and I will recommend that you take those exercises as your own practical work. Okay, so this 222, for example, you can go right ahead and then practice it, right? You can take it as a personal exercise and try to model it and compare and see if you are able to actually get the result. So for any exercise that you want to try out, you can always get to me. Okay, I think my email is in the description. You can always get to me. Even my WhatsApp is in the description. You can always get to me and then give me the exercise in question, and I'll give you the correct answers. Okay, so that you know whether you found the answer or not, if you don't have the book, obviously. Okay, if you don't have the book, to get the book, you can simply go and buy a copy on Amazon. Okay, or wherever you seem fit. Okay, good. Good, so it has come. We can go right ahead and continue. So to model this beam, the very first thing we want to do is to make sure that our units, as usual, are imperial. So I'll just go right ahead here to job preferences, okay, and then under units and format, we'll click on imperial to make sure everything is cool. Good. We have that settled. The next thing we want to do is to draw our beam, but in order to draw our beam, we need to set the scale, right? So what I would like to use here actually is let's go a little bit to something here. Uh, yeah, at the level of, I would like us to change the theme, okay? The theme that we are using as our background, so that the grid points can somehow be more visible. I hope you understand that. At this level, I'm not seeing the grid points very well. I don't know if you do from the video, but I am not seeing it very well. So what I want to do is to go to tools and to preferences in order to set the desktop setting and choose a different theme that enables me to see the grid points very well. Okay, so mm, I want to try a number of them here. No, no, I don't like that. No. Okay, no, it's still not visible to me. Yeah, why not? Let's take this one just for a start, okay, and then we'll come back to the default one later. Okay, so I'll accept that. Good. So those are our grid points, and you can see the way they are spaced, right? Good. So, in order to draw this inclined bar, we need a spacing of 24 feet following the X and 10 feet following the Y, right? So I'll just go right ahead and go to view and grid, and we'll go to grid step definition. Okay, following the X, we'll just put 24 straight, 24 feet, and then following Y, we'll put the spacing to be 10, so that we can use any square of our grid to be able to draw our inclined beam. Okay, so I'll apply that and close, right? So from 0 to here is 24, and then from, for example, 30 to here is 10, right? So it means I can connect any of these 2 points. If I connect here to here, I've drawn the beam, right? Because the distance from this point to this point is 24. The distance from this point to this point is 10 according to our grid. Okay, good. So let me just try to zoom in a little bit so that Yeah, let's take this 4 points so that we know that this is our beam, right? So I'll just go ahead and click on the beam. Again, in this case, the characteristics of the beam don't really matter, right? They don't. So we are good. We are good to go. So I'll just click first point, and then go right ahead here and click on our second point, and that is our beam. Okay. So we can confirm that. No, sorry, that was a mistake. Sorry about that. Come on, it's okay. We are there. Okay, so we can confirm that by simply going to dimensions line here and then measuring the distances, right? So I want the distance from here to here. It gives us 24, right? In fact, why all the stress? Why all the stress? There's no need to stress that much. You can see it from here, 0 to 24, and here 0 to -10. The distance is 10, the distance is 24, as we've been seeing. Good. That being said, the next thing that we want to do now is let's just put the supports first, okay? So for the supports, I think I'm not used to this theme. This theme was just necessary for me to draw that beam, okay? So let's go ahead and change the theme back to what it was. The blue, yeah, okay, accept. Good. So we are back. I like it this way. It's more interesting. Good. So we'll click on support, and here we say we have a pin support, right? We have a pin support. So we'll just choose our pin support and put it right here. Good. But here we have a different scenario. We have a support that is inclined at an angle that is perpendicular to the inclination of the bar, okay? But this bar is defined by 2 points, okay? So the very first thing we want to do is to first of all define we want to define the support in question, okay? So let's just call it roller, okay? And then roller implies that we don't want is one direction that we want to block. Let's say user, okay? Now we want that direction to be different, okay? The angle here we don't know, and we don't have time to measure angles, okay? But we can choose the node here, and we can take a reference node. For example, here the node number here is number 1, okay? And so if I take, I've just put my mouse there and it has already written node 1 there as a reference node. So let me just put node 1 there as a reference node, but then I'll explain to you what happens, okay, when you choose, for example, node 1 here as a reference node. Because when you choose a particular reference node here, you are already telling, you are already indicating the orientation of the support for any given other node that you will choose. Okay, so let me explain that. Okay, so we have, let me just add here, okay, close. So this is our support here defined. It is roller, okay? Now, what happens? The direction of this support is with respect to node 1. What does that mean? It means that if I want to place this support, for example, at node 2, okay, robot will automatically calculate what is the inclination from node 1, which is the reference, to node 2, okay? And then it will draw a support that is perpendicular to that orientation, okay? As if it rotates the support to be perpendicular to that particular orientation. The rotation is done anti-clockwise, okay? So if I put the support here, you can see that that's what happens. Okay, Robo has, because our reference node again in the definition of the roller support, our reference node was node 1. Okay, Robo calculates the perpendicular distance from node 1 to the node where I want to click and then places a support there. So just for you to understand, let's try it differently. If I have a different bar here, okay, let's represent a different bar here, for example, and I want to apply that very roller support. Why not another bar again, just to illustrate this principle so you can get it clearly. Okay, so If I go right ahead and I want to apply the roller support here, for example, how do you think it will be? It will be vertical, right? Because we have said UZ, okay? And UZ here, it will calculate what is the distance, I mean, the orientation from 1 to 3 is horizontal, right? So it wants to put the support perpendicular to this horizontal inclination, which will be vertical, as you can see here, okay? For this one, how will it be? This is the direction. The reference here is node 1, right? And when I click here, that is the way the support will be perpendicular to this beam. So I hope that explanation is clear. Okay, it will help you a lot. It will help you a lot to understand this the way I have explained. Okay, that being said, we don't need all of this. Good. It's not part of our structure. So this is our focus here. The next thing we want to do is to put a trapezoidal support, right? And as we can see, the support here is also perpendicular to the inclination of the beam, or is perpendicular to the neutral axis of the beam, right? So what we will do, we'll go right ahead here and first of all define the load. Okay, we'll add that. Good. That's done. And the next thing we want to do is to add the trapezoidal support, right? So we'll just come right here to bar and click on trapezoidal load. Okay. So trapezoidal load, what's our value for P1? Our value for P1 right here, sorry about that. Our value for P1 is 5 kips per feet. Okay. So we want it here to be 5. Our value for P2, I think, is 2, right? If we maintain the absolute distance, yes, it actually goes from 0 to 1. Perfect, right? So what do we want to do? We want to add this. You can see here that it is in the global coordinate system, this one, okay? And it is oriented towards Z. But we want it negative, right? We want -5 here and -2 so that it will point downwards and not upwards, okay? Mm. But is that orientation correct? Is that orientation correct? Let me show you. It won't be actually, okay? The orientation won't be correct. Let me show you. So if I add this and then we apply it to this particular beam, look at the way the loads are, okay? They are straight forward down, okay, but they are not perpendicular to the inclination of the beam. I want to show you the difference here. Maybe uh I should put this way and then maintain this other way just for your appraisal, okay, just for you to see. Are you seeing that this is in the direction of Z and this is perpendicular to the neutral axis here? So this is not the way we have to represent that load. Okay, so that causes us to introduce a new concept because we don't have time to be calculating what's the angle of inclination of this with respect to that in order to put the load properly. We don't have time for all that right now. Okay, so we want to introduce a different concept. But before that, let me delete this load. Can I just press Control? No, let me not take the risk. So we just go to load table, okay, and we'll take advantage to delete the self weight that would, robot automatically adds when you select a particular load definition type. Okay, we'll delete that by pressing Control X. Good, and we are good to go. Okay, all the loads have been deleted. Now we can work. Okay, so I'll just come right here to load definition. Okay, and under bar we'll take a trapezoidal load. The difference here is that we'll be using the local coordinate system, not the global coordinate system. So we have two coordinate systems here. The global coordinate system tells you it is the system for the overall structure, whatsoever structure that you will model here. This is the reference, the global reference for that structure. Okay, Z will always be in this direction, X will always be in this direction, Y inside, irrespective of the element that you draw. Okay, now local coordinate system, as the word says local, okay, is a coordinate system that is by element, it is per element, it is not It does not belong to all of the structure. Each element has its local coordinate system. And in Robo, and this is a principle of the finite element method, in Robo, the local coordinate systems of bars, okay, are in such a way that the x-axis is always in the direction of the neutral axis, and the z-axis, in the case of this 2D, will be perpendicular to that direction. Okay, so let me just try to represent that. There is something here that shows us, this is it right here, okay, that can display a local system for us. So if I click on that, you will see this. What you should know is that everything that is blue represents X, everything that is red represents Z, and everything that is Y represents that is green, sorry, represents Y. Okay, so if you see this, it's telling you that this system right here is a local system. It's not the same as this global system, but locally the x-axis is oriented in the direction of the neutral axis, that is in the direction of the inclination of the beam, and then the z-axis will always be perpendicular to that direction. Okay, so it is in this local z-axis direction that we want to represent our load because it is perpendicular to the orientation of our beam, right? Exactly. So I hope that's understood. Okay, so if I go back to bar here, I have to choose local, okay? Maintain it to negative, negative, as you can see, right? So that it can be opposite to this direction but applied on the load. And then I can add this load and come right here and apply that. And once that's done, you can tell the difference, right? So it is now perpendicular, uh, but perpendicular. I don't know what I wanted to say. Okay, good. So we have the loading there. We can see the loads. Okay, that is it from -5 to -2. Okay, so I think everything is set and we are good to go for the calculation to calculate the reactions, right? So I'll just go right ahead here and click on calculate. Okay. Let's go ahead. Let's go ahead. Okay, zero errors, zero warnings. I like that. It's perfect. So now let's check the reactions. Okay, so we'll go to results and we'll go to diagrams for bars. We'll just go ahead and activate the reactions, right? So just show me all the reactions. No, apply and close. So what are the reactions here? Here we have 20 and 48 for the pin support down here, and here we have 15 and 36. So let's check that out. Unfortunately, in this document, on the answers right here don't have the answer to this particular exercise, but then I'm having the marking guide, okay? So the marking guide here, this is the exercise here, and we can see the answers right here, okay? So at the level of FB, we have 39 keeps, okay? So it is because it is the 39 that is oriented in this specific direction, okay, in this direction. So we can calculate what we can calculate the course of that to be able to determine what we are having here. If it's correct, we can get the cos to see whether the cos corresponds to 15 or 36, and we can also get the sine to see whether it corresponds to that. So for that, we can just go here. You will see that we have 24 feet this way and 10 feet this way, right? So 24 and 10 will give us a hypotenuse of 26. If you do the square root of 24 squared plus 10 squared, it gives you 26, okay? So to be able to get the sine of 26 of the angle of inclination here, it will have to be sine, right, which is opposite divided by hypotenuse, okay? So it will just be 10 divided by 26. So if we do 10 on 26 times 39, it should give us one of our answers if what we did is correct, right? So let's do that. 39 times 10 divided by 26. So it should give us 15. Are you seeing that? And this is our 15 right here. Okay. And then the other one, 24, 39 times 24 divided by 26 should give us 36, right? Which is the other answer we are having right here. Good. So what about we have negative 20 and 48 at the level of the x. Here we have 20 and 48. Okay, at the level of x. So it depends on how they oriented there. Okay, as you can see here, the ax here is oriented how? It's oriented opposite. So it's normal that it should be 20. Our own positive direction is in this direction, right? So it's normal that we have negative 20. So it's exactly the same answer. Okay. So I think that does that for exercise 4. I hope you learned a lot, and see you guys in the next exercise.